we're going to do some notes on something called percent composition and empirical formulas. Let's begin. So just a review, we kind of already know percent composition. We did talk about this, I think, in maybe unit 1 or 2, but you already know how to do this. This is that mho over mach thing. So here's a quick example. What is the percent composition of chlorine in sodium chloride? You take the formula, NaCl, and you break down the molar mass, and then after you get that molar mass figured out, you just put the small number on the top and the grand total on the bottom. So here's an example for percent chlorine. So you'll notice that I put the mass of chlorine on the top and the grand total of the compound on the bottom. So you get 60.7 for this guy. Feel free to pause the video at any time if people are still writing down their notes. Otherwise, I'm going to move on. So here we go. So let's dig a little deeper on these percents. Why don't you pretend that you have exactly 100 grams of sodium chloride? Of that 100 grams of sodium chloride, how much do you think would be chlorine? Well, if you go back to the previous slide, we know that 60.7% of sodium chloride would be made of chlorine. So if you come back over here, if you have exactly 100 grams, wouldn't that be exactly 60.7 grams? Percents are based off of hundreds, right? Alright, so in 100 grams of sodium chloride, you would have 60.7 grams of it being chlorine. So that's pretty easy. But I know you guys kind of suck at percents, so we're going to dig a little deeper. Instead of having exactly 100 grams, right, this math was easy. Instead of doing exactly 100 grams, why don't we switch things up a little bit? What if you have 14.2 grams of sodium chloride? You're not always going to be working with exactly 100 grams of stuff. So how would you do this? Alright, just remember the basics of percents. So you know that 60.7% is going to be chlorine. You just don't know what part of this 14.2 grams is chlorine. The grand total you know, so the total mass is 14.2, and you see me putting that on the bottom. You don't know what part of the 14.2 grams is chlorine, but you have that percent. So this is kind of like showing you how to do your math in your lab. This is how you got your theoretical yield, right? It's the same idea. So to solve, what we're going to do is we're going to do the opposite of multiplying by 100. Opposite of multiplying is dividing by 100. So that gets rid of this. But you see these equals? Whatever you do to one side, you have to do to the other side. So we're going to take that and we're going to divide this by 100. Alright, that'll change your percent into a decimal. 0.607. That's equal to x over 14.2 grams. Alright, now you just need to solve for x. A little bit of algebra. In order to get x by himself, denominator has 14.2. Remember, denominator means divide. So we're going to do the opposite of division. We're going to multiply by 14.2. And whatever you do to one side, you have to do the other side. 14.2. So to solve this, take the decimal form of the percent and multiply it by the total mass. 0.607 times 14.2. I get 8.6194. Now with sig figs and all, we should probably be reporting 3 sig figs. We got 3 sig figs here, 3 sig figs there. So the final answer should be 8.6, and it looks like you need to round that up. So 8.62 grams. Alright, so there would be 8.62 grams of chlorine in 14.2 grams of sodium chloride. Alright, so you're probably wondering, why are we learning about percents? What has percent composition got to do with anything? Well, those of you who are interested in forensic science, you may want to kind of listen up. A lot of times in forensic science, we have to figure out what a mystery compound is, maybe in a crime scene. And a lot of times what they'll do is they'll take a sample of that mystery compound and they will push it into something called a mass spectrometer. The mass spectrometer can basically separate the various compounds into their elements based on their mass. So the heavy particles will be thrown into the machine and they will not be pushed very far because they have a high mass. And the low mass compounds, they'll be pushed much further through the machine, and so you can analyze basically the percent of particles that are heavy versus the percent of particles that are light, and through that analysis you can actually figure out what the mystery compound is and what its formula is. So how do we do that? We can figure out the formula just from percent compositions. So let me show you how we do that. So you're going to want to start with a simple example. Since we are working with sodium chloride, you already know that 60.7% of sodium chloride is chlorine, and the remaining percent, 39.3, must be sodium. Obviously, when you take 60.7 and you add 39.3, you're going to get 100%. Well, let's see if we can take those 2% and turn that into the formula NaCl. Alright, so you may want to jot down in your notes, jot down this percent, 60.7, and that is percent of chlorine, and 39.3, that's a percent of sodium. And let me show you how you can actually get to the formula just based off of the percent. So write down this for step 1. The first step is that you have to assume that you have 100 grams of this mysterious compound. Because if you assume that you have 100 grams of the mystery compound, it turns your math into a very, very easy calculation. So if you have exactly 100 grams of sodium chloride, look at your percents. Remember, you wrote down your percents? If you have 100 grams of this mystery compound, that means you have 60.7 grams of chlorine and 39.3 grams of sodium. So step number 1, you basically change your percents to mass. Step number 2, you're going to change those masses that you just got into moles. So chemical formulas are based off of mole ratios. Sodium chloride has 1 Na for every 1 Cl. So for every mole of Na, there will be 1 mole of Cl. So in step number 2, you need to convert the masses into moles. So the first mass was 39.3 for Na, and then you have 60.7 grams for Cl. So you see how I did my work? Always cross-cancel your units, grams and grams, changing it to moles. Same thing with chlorine, grams, grams, convert it to moles. Watch your sig figs. You have 3 sig figs here, 3 sig fig here, so you're probably going to want to reduce to 3. That 0 at the end here is going to need to turn into a 1. And here we go, we got 3 sig figs here. Again, that 0 right here is going to turn into a 1. So, check it out. This means that you have a 1.71 moles of Na for every 1.71 moles of Cl. Well, I know that we don't write formulas like this. You would never see the formula for sodium chloride looking like this. You see the subscripts there? So in step number 3, we are going to take these silly ratios, the ones that really don't make sense, and we're going to divide by the lowest valued number of moles. Now, since they're both the same, you guys can see that that's a 1-to-1 ratio, and that's easy. But what if we don't have a 1-to-1 ratio? So this is a very simple example. I just wanted to show you that you can take the percent composition of sodium chloride and get the formula. But let's try something a little bit more difficult. Let's try something where you have a 1-to-2 mole ratio, or maybe even something that has 3 elements, like Na has 2, C is 1, and O is 3. You still should be able to go through the same process. So let's review that process with a specific example. Here we go. Here's your next example. Let's pretend now that you have 104.9 grams of iron and 45.15 grams of oxygen. So this compound contains iron and oxygen. You'll notice that you don't have a percent. Remember, step number 1 that I showed you guys before was to change your percents into mass and just assume that you have 100 grams, right? So you just change your percents to mass. Well, what do you do if they gave you mass and not percents? Well, I'm sorry, but you have to have those percents. You cannot start the problem until you calculate your percent composition. So that's the very first thing that we're going to have to do. So in order to find the percent composition, you're going to put the mass of the element, so this is percent iron, mass of the element on the top, mass of the compound on the bottom, multiplied by 100. So it looks like there's 69.9% iron. And then here you go with your oxygen. There's the total compound again. And it looks like you have 30.1% of oxygen. So we have our percents. That was the very first thing that you had to do in this problem because they didn't give you percents. All right, step number 1. Assume you have 100 grams. All you're going to do is change the percents into grams. So now we have 69.9 grams of iron and 30.1 grams of oxygen. Look back at your notes. What is step number 2? What do we do now? You need to change those masses into grams. So you see, I'm doing the same thing. I'm converting. Notice that the mass down here, the molar masses, are just the mass of one of the element. Okay, and I already rounded my answers to 3 sig figs. So now look at our moles at the very end. This doesn't look like anything very easy to use, 1.88 to 1.25. So look back at your notes again. What does step 3 tell you to do? In the previous problem, it was really easy. It was sodium and chlorine, right? And it was obvious that it was a 1-to-1 ratio. This time, it's not very obvious. So here's the rule. Divide by the lowest number of moles present. The lowest number of moles is 1.25, right? Because this value is a little higher. So 1.25 divided by 1.25, that's easy. It's 1.5. 1.88 divided by 1.25 gives you 1.5. So here's our new adjusted mole ratio. Now, does that make any more sense to you? Well, we still wouldn't write the formula like this, would we? Iron 1.501? Yeah, it still doesn't look very nice. So sometimes what we have to do is manipulate the ratio so that we get perfect whole numbers. So here's my question. Can you think of any way to make both of these subscripts whole numbers? Alright, step 4 is only if it's necessary. When you don't have a clean, perfect whole number ratio, you are allowed to manipulate the ratio so that you get perfect whole numbers. So how can I change this ratio into perfect whole numbers? You can either divide or multiply both of these by 2. So if you can multiply by 2. And then I suppose you can divide by 0.5. Sorry. So if you multiply by 2, that 1.5 will turn into a 3, the 1 will turn into a 2. Those are your whole numbers. So that's a much nicer formula to write. And so what you have for your final formula is Fe2O3, iron 3 oxide. Okay, so at this point we are done with the PowerPoint. So we're going to switch over to the worksheet. So I did give the sub a copy of all of the worksheets that you're going to be using for this unit. Okay, so the worksheet looks like this, but I'm sure you already know there's not enough room to do any work on this, so you're going to probably want to pull out a separate sheet of paper. So I know this looks like a lot, but once you get started you're going to realize that most of these questions are really simple and quite easy to solve. So question number 1, that's easy, it's definition. Question number 2, describe how to find the percent composition. Again, that's pretty easy. Question number 3. You have determined that a compound is composed of 0.3 moles of carbon and 0.6 moles of oxygen. What must you do to determine the mole ratio of the elements? So look back through your notes. Once you get to the moles and you have like a mole ratio, technically that's what this is a mole ratio, how can we make that mole ratio clean, like a perfect whole number ratio? I think you guys know what to do there. Let's see, number 4. The mole ratio of carbon to hydrogen to oxygen in a compound is 1 to 2 to 1, respectively. Give an example of a molecular formula for the compound. Alright, so this is where I wanted to review something that was not covered in the PowerPoint. So I'm skipping 1, 2, and 3. So just make sure you have a little bit of room in your paper, and we're going to talk about this problem real quick. Okay. So there's something I didn't teach you in your notes that you kind of need to have at this point, and it is the definition of an empirical formula versus a molecular formula. So we're going to cover that real quick. Okay, an empirical formula is when the ratio is at its lowest common multiple. So a great example would be, say, let's see, H2CO3. This would be a 2 to 1 to 3 ratio. And you see how you can't really reduce this any lower. It's a 2 to 1 to 3 and it's non-reducible. So an empirical formula, you could say, is the lowest whole number ratio for a formula of the elements in a formula. Okay, now in comparison, a molecular formula can be a multiple of the empirical formula, kind of like this. What if it was H4C2O6? So that would be a 4 to 2 to 6 ratio. Do you see how this is a multiple of that ratio? So a molecular formula is a little bit different. Molecular formulas can be reducible. So their ratios, so the ratio of the atoms in the compound can be reduced. Alright, so that is just a quick definition. Empirical formulas are always the lowest whole number ratio, and molecular formulas, they can be reduced further. So coming back to this question, you have a mole ratio that's 1 to 2 to 1, and they said give an example of the molecular. Well, just like double everything, 2 to 4 to 2. You could also do like 3 to 6 to 3, 4 to 8 to 4. I think you guys get the idea. Alright, there is another question in here that I wanted to review with you. Let me see if I can find it. Let's see. I think it's... Okay. Question number 14. So I know I'm jumping around a little bit, but hopefully you can make some space a little bit in your notes so that you can make this fit. Alright, so here we have a formula, CH3O. That's empirical, it's a 1 to 3 to 1. But then you see this little tidbit of information at the end. It says that the molar mass of the molecule is 62 grams per mole, and they want the formula of the molecule. Typically, the molecule is a multiple of the empirical, right? So in order to figure out what the true formula of the molecule is, we kind of need to know what the mass of this is. So what I would do is I would go to my periodic table and I would get the molar mass of this guy first. Okay, and then we just add all this up. 12 and 3 and 16. This guy's mass is 31 grams per mole. So the empirical formula has a molar mass of 31 grams per mole. Now, if the molecular formula has a molar mass of 62, I think you guys can see that 31 goes into 62 2 times. So that means that the empirical formula must be doubled. So the molecular formula would just be double the empirical, C2H6O2. And that would be your final answer. Again, that was question number 14. Alright, at this point, I feel that you probably have enough information to be comfortable to work yourself all the way through all of these problems.